All right, so we have been looking at gas properties like Boyle's law, Charles' law, combined gas law. We also looked at ideal gas law and how to deal with moles and gases at standard temperature and pressure, and the idea of Avogadro's principle. Today we're just going to look at two other laws, Graham's law, and we're looking at Dalton's law of partial pressures. So Graham's law is going to look at how fast gases are traveling, and partial pressures is going to look at mixtures of gases. So let's get started. We're going to look at Graham's law first. So let's say we have some molecules here bouncing around inside this container. We say they're moving around, pretty quickly. They're colliding, creating pressure. We say they have energy of motion. So kinetic energy is the energy of motion. Abbreviate that KE. And that equals 1/2 mass times velocity squared. So if we look at this equation here, we see that mass is to the first power and velocity is to the second power. So we can kind of figure out by multiplying mass times velocity squared, or we can just measure the temperature. I'll abbreviate that temp. Temperature is a measure of the average kinetic energy that a gas sample has. Higher temperature, of course, more energy. And that's something we've already looked at. So what did Graham do? Graham looked at the relationship between mass and velocity. So for a given temperature, the kinetic energy remains constant. I'm going to just draw a line saying that doesn't change. If mass goes up, then velocity has to go down, and vice versa. But how are they related? Well, mass being to the first power, velocity being to the second power, it actually looks like this. The velocity of a gas is indirectly proportional to 1 over the square root of m. Because if I square root this, I need to square root this one here. So this means as mass goes up, being on the bottom, velocity will actually go down. So if we were to compare two gases, one with a smaller mass and one with a larger mass, and they're at the same temperature, the one with the larger mass does have the lower velocity. But remember, it is related by the square root of m. So what's Graham's law? Graham's law states that the rate of effusion of a gas is inversely proportional to the gas molar mass. Now, effusion is like the rate of gas escaping from somewhere. And his equation is rate A to rate B equals the square root of molar mass B over molar mass A. I want to convert this equation to something a little more useful to us. I want to say the velocity of gas A is to the velocity of gas B as the square root of mass B over mass A. You see how this is inversely proportional. The A is on top here, it's on the bottom there, and it's on the bottom here, and it's on the top here. So this is the Graham's law I would like you to copy down, because we're going to be looking at the rates of velocities. Let's look at one example here. What if I wanted to do the ratio of the velocity of chlorine molecules to argon atoms? So I'm going to write that as the velocity of chlorine over the velocity of argon. That's going to equal the square root of the molar mass of argon divided by the molar mass of chlorine. Okay, so now chlorine, though, is a diatom, so I'm going to put a 2 here, and I'll put a 2 here also. Okay, so we got to get their molar masses from the periodic table, and we got to make sure we do 2 chlorines, because it's a diatomic. Okay, so let's go ahead and solve this. So I'm going to rewrite this. The velocity of chlorine over the velocity of argon is equal to the square root. Now, of course, I go to the periodic table, and I can get the molar mass, okay, of argon, okay, from the periodic table. And that is going to be 39.948. Now, again, your periodic table might be a little different than mine. And then I'm going to divide by twice the mass of chlorine. So that's 70.90. And I'll divide those two and do a square root. And my answer comes out to be 0.75. There is no units with this since it is a ratio. And when you do the simulation today, we're going to round to the tenths place, so that would be 0.8. So that's Graham's law in a nutshell. Not too bad. We just want to know basically the ratio. Notice how I'm not solving the left side, I'm just solving the right side. I want to know what the ratio is. Okay, next questions here. Dalton's law of partial pressures. Dalton's law of partial pressure is just for a total pressure of a gas when you have other gases that make it up. It's a pretty simple principle. So if I have more than one gas that makes up a pressure, the total pressure is just the sum of all the individual pressures. So pressure total equals pressure 1 plus pressure 2 plus pressure 3. So it's a very simple law to look at. We're going to look at 3 applications of this, which are also pretty simple to do. First example, a gas is composed of 3 gases, 2.3 atmospheres hydrogen, 0.9 atmospheres nitrogen, and 0.5 atmosphere of sulfur dioxide. So I just want the pressure total. I'm just going to add them up. Pressure total is 2.3 plus 0.9 plus 0.5. Okay, and that gives us a total of 3.7. And of course, that's atmospheres. We're not going to write that in our simulation, though. When you do it, you'll just write 3.7 and round to the tens place. Each one of these are called partial pressures. They are part of the whole. So a partial pressure of 2.3, a partial of 0.9, and this is 0.5. And that's why it's called Dalton's law of partial pressures, because each pressure that makes up the total is part of it. Okay? Next, what if we have a wet sample of a gas? So if we have water mixed in gases, that happens pretty frequently. So a wet gas sample of nitrogen has a total pressure of 105 kilopascals. If the partial pressure of the water in there is 7.5 kilopascals, determine the dry pressure. So I'm just going to say pressure of nitrogen. Notice how I'm writing as a diatom, although you don't have to right now. That's going to equal then 105 minus 7.5. I'm just going to subtract out the water pressure. That's all I got to do. And it's 97.5 kilopascals as the result. Now, why do I do that? Well, if the total pressure is nitrogen and water, and if I just want nitrogen only, just take away the water pressure from it. And this is going to be the partial pressure of the nitrogen gas or the dry gas. Okay, since there's no more water considered in it. So all we're doing is subtracting that out. All right, in our last example, example 3, a gas sample has a pressure of 66.7 kilopascals, and it's made of 9.5% helium. Determine the partial pressure of helium. So all I got to do here then is take 9.5% of the 66.7. So I'm going to take 0.095, and I'll multiply that by 66.7. And that'll equal 6.3. Notice how I'm writing out to the tenths place, but I'm not writing units. The answer for this would be kilopascals, of course. So when you do the simulation today, make sure you record everything out to the tenths place, but do not include units when you write them. Okay, so that's the third application. And just think of this, if the total pressure is this, and we know helium is only 9.5% of that. If you remember, the word of means multiplication in math, so I got to take the decimal percent though. So 0.095 multiplied by 66.7 gives me 6.3. So you're not going to take 9.5 times it, you got to take 0.095. So you always got to remember to divide your percents by 100, okay, before you use them. Okay, that's our lesson of the day. Please try the simulation. Let me know if you have any questions.